Sorry.
Alright, so if they say sketch and graph and find the limit, so they want us to look at y equals 1 divided by
Bag of chips.
x squared. So you can sketch that graph.
There is no limit.
How do you know to graph it like that?
Because I showed you on the calculator.
Oh, okay. So what is
Or
the
you gotta pick
equation?
a few points. Okay, so this is the limit as x approaches 0. Well, here's 0. So as I come in this way and pick numbers that are closer and closer to 0, my inputs, right, my x values get closer and closer to 0. From this direction, they get closer and closer to 0. What's happening?
Bigger.
To what?
Why?
If you traced it with your finger, the blue lines, they would both be going toward positive infinity. They're both going to go up towards positive infinity. Now, some people, you could say something like, because positive infinity isn't really a number, you can make some arguments that it does not exist there, but because both sides of it are going towards infinity, we would say it's more about the behavior is the graph increases forever. If I ask you to sketch this graph, what was it? Is it 1 divided by sine of x?
Sine of 1. Sine of
Sorry,
1.
sine of 1 divided by x, thank you. Yo, I want it. I'm going to go into radian mode, make sure I'm in radian mode when I graph it. Let's see if we can see it. So it kind of does that, right? And if I zoom in a little bit,
Whoa!
so you kind of think that as we get closer and closer, so I could go negative 0.1 to 0.1, and if we zoom in here, maybe like negative 2 to 2.
It's like a heartbeat.
Even though I'm zooming in more and more, it's actually getting worse, right?
That's bad.
Yeah. Very.
How would you draw that?
Just do something like that.
I want to like that.
What would we do? Standing.
Wait, how do you know that?
Yeah.
Oh, because it's just.
Do not resuscitate.
Danny, this thing is oscillating up and down so much that it doesn't settle down on a specific number. So these are some things that can happen. So on this graph, it's it's 0 if x is an integer. So at 1, 2, 3, at 0, negative 1, negative 2, I have these dots. So on the integers, my outputs are 0. On all of the integers, my outputs are 0. 0, the integers, right? The counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, negative 1, negative 2, negative 3. But it's 1 if it is not an integer. So then, here's where 1 is, right? So it's looks kind of like a chain.
Wait, is that supposed to be directly above the point at 1?
Yeah.
Yeah.
There's like 1, 2, 3.
What?
So all these numbers are now you're approaching 2. So here's where 2 would be located. This is exactly the same problem as what we've been doing today. So what's the limit?
1.
Only at specifically 2 would it drop down to an output of 0. But at 2.1, 2.01, 2.001, 1.9, 1.99, 1.999, the output is 1. So that's your limit. Conditions under which limits do not exist.
Wait, go back.
Oh, wiggly line.
Alright, so you can copy these 3 things down. This is when limits do not exist. So this is like the absolute value problem we did. It increases or decreases without bound, going to infinity or negative infinity. So that's that argument. They both were going up to infinity, but you can also have graphs that go like this. We looked at them in 2, 6, 2, 7. You could have one here and one here. So if I asked you to look at 0, one side of the graph is going to infinity, one side is going to negative infinity. So that's very similar to 1. And then the oscillation one that we talked about, the sine function that went up and down. So again, this is the same one. We've already done this. This is absolute value over absolute value. And you can type this in your graphing calculator if you want. It's the absolute value math, number, select absolute value. So what was it? X plus 1? X minus 1, thank you, is absolute value. And
Just plug it into the calculator.
we're dividing by, make sure you put parentheses around X minus 1. Yes, so you can graph them. Those of you, oops, I gotta zoom
I can do
in.
absolute value.
Math, slide over to number, absolute value. Those of you that have a slightly older calculator, the programming on it, you may see this like spike in the graph. It doesn't know what to do, but that's what we talked about earlier. You have one here. Whoop. Switch colors. So at 1, you have one there, and you have one down here. So what's the value? What's the limit as x approaches 1?
Wait, so it doesn't actually like go up like that?
No, does this.
Okay.
Does not exist. If so, why? Well, if you traced from both sides, your fingers would not come together. What about the square root of x? So remember, a square root graph kind of looks like that, right?
Yes.
Oh, why did I do it like that?
Doesn't it come from the
I
section?
did 4. Sorry. So it goes like this, right? Square root of x graph. Well, they want me to get close to 4. Well, are there any holes or asymptotes in that graph?
No.
No. So as long as I'm picking an x that's in the domain, right? I can just go ahead and do the square root of 4 and I get a 2. So that's the limit.
So the limit is 2.
Yep, here would be the output dot. So if you pick 4.1 and you pick 3.9 and you pick 4.01 and you pick 3.99, you're just going to get closer. You just follow the blue square root graph line. So when I put the square root of x graph in here, don't look at the 4, 2 part. What are the blue numbers on either side of the 2? What are those numbers getting really close to? 2. Now, it happens that when you put the number in, it will sometimes be the limit. But if you get a 0 over 0, we have to do something different. This one just happens to work.
So like,
We can do this cosine of 1 over x, right? So just remember when you're graphing these things, cosine of 1 divided by x, you want to make sure you're in radian mode. If you graph it, what's it doing in there?
Oscillate.
It's oscillating. If we look at the table and get close to 0 and go pretty small here, 0.001,
Close.
oh, I gotta go up a little bit.
so like 1 to negative 1?
No, because this one is positive 0.9, that's negative 0.8, positive 0.5, positive 0.5, negative 0.8, positive point, right? They're going positive or negative as I get really close. It's still, you can see it going up and down, up and down. It's oscillating. This real quick, it was something again like that one we saw earlier, like that. All right, 1 over x. Well, we should know that. We just did 2, 6, 2, 7. So if you graph it, you have a graph here, and you have a graph here, and you actually have a vertical asymptote right down the middle at x equals 0. Well, that's telling you that you can't plug in 0. So this goes back to the question that was earlier, right? So plug in 0. Are you going to get anything?
How do you know there's a vertical?
No,
axis?
sir.
Because you can't use 0 on the bottom. So what's 1 over 0? Type in 1 over 0, what happens?
Error.
Error. That error does not mean that the limit does not exist. What tells you the limit does not exist here?
We're going to infinity.
At point 1, 0.01, 0.001, my graph is going to positive infinity. If I do negative 0.1, negative 0.01, negative 0.001, my graph is going to negative infinity. So if you traced it with your fingers, one graph is going up, one graph is going down. So your fingers aren't coming together, but they're also exploding in different directions. So there's no limit. Absolute value graphs. Again, absolute value has continuous domain. So you're just going to move over one V-shaped graph. Are there any holes or restrictions on an absolute value graph? No. So this is one of those problems. Just plug in 1. What do you get? When x is 1, well, everything's going to be coming right to that blue dot. So the output is 0. And I know I'm rushing, but we're trying to get done. Sine of x, 0, pi over 2, pi, 3 pi over 2. What's the domain for a sine curve?
1.
Domain,
Oh, 2 pi.
negative infinity to infinity.
Ah.
I can put anything I want in for x, right? It oscillates, so we have oscillation, don't confuse that though. But it just goes up and down forever, oscillates forever. So the graph looks something like this, starts at the midline, goes to maximum, midline, minimum, midline. So it goes right there. What they want you to do is approach pi. So if I get close to pi, where are your outputs?
0.
So you trace your fingers, you just kind of do this, right? And you're bringing them in, and you're getting closer and closer to 0. After today, we actually start to learn some algebraic techniques for finding the limit. But today, just remember graphs and tables. That's all we used.
Wait, so